Today we will discuss Prigogine's principle of minimum entropy production. First, we will consider a one component system in which both temperature gradient which we will represent by xth, as well as the concentration gradient. We will represent that by xm. Suppose they exist in this system, both these, that means the temperature gradient as well as the concentration gradient. Now, in the vicinity of equilibrium, the entropy production per unit time is given by, for example, for two fluxes to force system. That means we are considering here first the temperature gradient and concentration gradient. They are actually occurring in the same system, and mathematically we can write this dis upon dt, which is simply the entropy production per unit time. If we take into account two fluxes and two forces, then we can write J thermal x thermal plus Jm xm, it will be greater than J. So this will be our equation first, and we can develop the linear phenomenological laws. And the linear phenomenological laws are simply, we will write here, is J thermal be equal to L11 xth plus L12 xm. This is equation second, and Jm, you can take this as mass flux or matter flux, so it will be due to concentration gradients, so it will be represented by this phenomenological law. That means L22 x M. This is equation. Here, this L11, this is simply coefficient of thermal conductivity. And this L22 is diffusion coefficient. L12 is coefficient of heat associated with concentration gradient. And similarly, L21 is coefficient of mass flow, and it is associated with the temperature gradient. So we have actually taken two fluxes and forces here. Basically, one is due to mass flux, other is due to the temperature or thermal flux. Now, one more point we have to see here is that we have to remember that stationary states may be characterized by an extremum principle, which basically states that in the stationary state, the entropy production has its minimum value. If we compare it simply a table with some auxiliary conditions, and that have to be specified in each case. Now this is very important here, this point. What is this extremum principle? So we will now use equations 1, 2 and 3. We will use all these three equations, and also the Onsager reciprocal relation. Reciprocal relation, which is L12, that means this coefficient is basically equal to L21. So if we now take the entropy production and write it as full relation, that means entropy production per unit time will be equal to, simply we will use the second and third into first, so we will write L11 xth plus L12 xm, and it is simply multiplied by x thermal, plus we are simply inserting the values of J thermal and Jm, that means the thermal flux and the mass flux. So we will write here also L21 x thermal plus L22 xm and multiplied by xm, which is greater than 0. So this is suppose equation 4, and this will be equation number 5. So simply we will give this x thermal back to the each term, so it will be L11 x th square plus L12 xm xth, plus similarly for this case we will give this term back to these two terms, that means it will be L21 xth xm plus L22 xm square, so it will be greater than 0. This is equation 6. Now we know basically this relation here, which is this L12 is equal to L21. So if we focus on these two terms here, that means they are actually the same terms. So we can write then, in place of these two terms, we can write this entropy production per unit time will be simply equal to L11 xth square plus this will be simply 2 times, so we will take one of the coefficients because L12 is equal to L21, so we will write suppose L12, it will be xm and xth plus L22 xm square greater than 0. So this will be our equation 7. So if we take the derivative of this equation with respect to xm, simply taking derivative with respect to xm. Also we will consider this at constant xth. We will consider this xth as constant. So from equation 7 we will simply write the first the derivative with respect to simply xm. We will insert here dou upon dou xm, and we will write this entropy production per unit time here. So this will be simply equal to dou upon dou xm into this L11 xth square plus dou upon dou xm 2 times L12 xm xth plus dou upon dou xm L22 xm square will be greater than 0. This is equation 8. So we have basically taken here a condition where this xth is constant. So if this is constant, this L11 is also constant, so it is differential with respect to xm will be 0 plus. Okay, so this term twice L12 and xth, they are constant, they can be taken outside. We can write xth and it will be simply differential with respect to xm, so that means equal to 1. Okay, similarly for this case L22 is constant, we will take it outside and it will be dou upon dou xm, and this will be xm square, it will be greater than 0. This is equation 9. So it is easy now to solve this. So it will be 2 times L12 xth plus it will be x raised power n, so it will be 2 times L22 and x raised power 2 minus 1, that will be simply equal to xn. So basically we got this term here, so it will be greater than 0, equation 10. or we can simply take out this 2 outside and we can write simply L12 xth plus L22 xm, it will be greater than 0. So this will be 11. But we know this L12 xth plus L22 xm is basically equal to, this is equal to Jm. So this, the entropy production, that means the derivative of rate entropy production per unit time with respect to xm is basically equal to 2 times Jm. This is very important relation here. That means we can say this first derivative is basically having a positive value. But for a steady state, we know, this is very important here, we know in the steady state this Jm is simply equal to, that means the mass flux is basically, or matter flux is equal to 0. So if this is equal to 0, that means the first derivative with respect to xm of the entropy production will be equal to 0. That means it will imply dou upon dou xm dis upon dt will be equal to 0. So now if the first differential of a quantity is 0, that means it is basically a stationary point. Now these stationary points are of 3 types. That means it can be a maximum, minimum, or an inflection point. So to find out this, whether it is a minimum or a maximum or inflection point, we will do the second derivative also. So we will write dou square upon dou xm square, the entropy production per unit time. We are taking simply the second derivative. So we will take the second derivative of this equation. Suppose this is equation number 12. This is equation 12. So here we will write simply dou upon dou xm twice jm, but here you have to remember we are taking xth as constant. That means at constant xth. Okay. So it will be simply equal to, we will reintroduce the value of jm here. So 2 can be taken outside, so it will be 2 dou upon dou xm, and we will introduce the values of jm again here, which is L21 xth plus L22 xm. So here you can see that this is constant, so this is whole constant, it will be 0. So it will turn out to be 2 into 0 0 plus, that means only this quantity, that means it will be simply equal to, I will write it as a whole, that means 2 into 0 plus 2, and L22 is constant, so we can write it as dou xm upon 2xm. So this will be equal to 1. That means this comes out to be twice L22. So this term will go, this term will remain. So that means we have got the second differential here. Xm square dis upon dt is basically equal to twice L22. So we will number these equations. So this will be equation 13. So this will be, suppose now, equation 14. Here the second differential is, because this is a constant, so this will be positive. That means L22 is positive because it is a coefficient constant, so it is positive. That means the second derivative is also positive. That means this extremum is simply a minimum. That means we have found this as to be a minimum. This is very important point, because the second differential has come out to be positive also. That means are greater than 0. Now what is the significance of this? Basically this statement furnishes the mathematical statement of Prigogine's principle of minimum entropy production. Basically, according to this, now according to which at the steady state, all the flows corresponding to unrestricted forces they basically vanish. So this is very important. Sometimes a graph is also shown for this. Suppose if sigma is the entropy production, that means dis upon dt, entropy production per unit time. If we plot this graph, we will take it along the y-axis, and suppose this is xth, so it will be, so first we will plot it with xm, because we have taken xth as constant. Basically